and get started. Our first speaker is Micheal Austin. Micheal Austin is Vice President of BYD America. BYD Motors is the largest electric bus manufacturer in the world with over 1,300 battery electric buses completed that run entirely off of battery power lasting up to 24 hours on a single 2 to 4 hour charge. Micheal has worked in the rechargeable battery industry for almost 25 years and has worked 15 of those years at Motorola and as the Global Energy Sourcing Director. Micheal has received a master's degree in mechanical engineering and has 25 U.S. patents, most of which have to do with batteries. So Micheal, with that, I'd like to turn things over to you to give your presentation. Thank you for joining us today.
Thank you, Katie, and thank you, attendees. In the interest of full disclosure, I'm a battery guy today masquerading as a bus expert. I've been asked today to talk about the global advances in electrified public transportation. I'll focus my comments in bus technologies. I'm going to do my best. We have 15 slides and about 15 minutes for my part, and I don't want to take up any of the other presenters' time. But I want to do my best to give you a hint of our visions and of the market and specifically our design philosophy. So this first slide is showing a BYD electric taxi and electric bus. I need control. Okay, I've got control. Got it. The second slide shows some of the electrified transportation gains. I think buses will be of most interest, electric buses specifically, in the regions where we're seeing a lot of consumer interest in EV sales. And right now, China, the United States are leading the way in some of those areas of interest. The global bus market segmentation, we're focused mostly in the transit buses. And within that, you have the BRT, the bus rapid transit, you have conventional transits. BYD specifically is targeting the battery electric transit markets. And if you look at what 2020 will look like, so this is by Frost and Sullivan, and the bubbles are the size of the replacement market in that year for heavy-duty transit. So in the United States, in North America, there's about 75,000 in the bus rapid transit fleet. They're replacing there'll be 6,400 buses replaced in 2020. The North America market alone only owns 2.5% of the global heavy-duty transit bus market. So we're looking to leverage other markets to drive our component spend leverage and our manufacturing scale. China, by far, is the #1 market in heavy-duty bus transit, having 26% of the global share. In 2020, it's forecasted that they'll replace 73,000 buses in that year. Latin America will also be up there, as well as Africa and India. So those are the markets that are really driving some of this heavy-duty bus transit markets. And Frost and Sullivan predicts that 15% of those by 2020 will be electric buses. So what we're talking about literally is about 40 to 55,000 electric buses that will be replaced or will be replacing older technologies in 2020. So this kind of just gives you a feel of how we see the market playing out. And you really want to play in a lot of these markets in order to leverage your component spend and your manufacturing scale. When you look at the way Frost and Sullivan lines up the OEM starting in 2012, you don't see a lot of electric guys up there. Volvo does play in a number of the markets. And then Frost and Sullivan listed BYD, which BYD only plays in the battery market, and we are the only OEM that's vertically integrated with a battery and in-wheel hub motors for our products. Today we have about 4,000 booked orders, and those are coming out of China alone. So you were seeing a lot of scale out of those markets. So I've been asked to kind of explain the BYD design philosophy and specifically the BYD bus and the technology behind it. BYD has an all-aluminum frame, and we custom build that for each transit. Obviously, the requirements by the transit company, what type of seating, what type of air conditioning is all part of that bid for the RFQ. We have standard in-wheel hub motors, and they're driven by an energy storage system that we use. We use Iron-Phosphate chemistry, about 324 kilowatt hours of iron phosphate, with a single nighttime charge, or a single charge. Our range, we say, is 155 miles. Some of our customers have tested farther than that. We had Antelope Valley recently do some testing and said they were running up to 250 miles on a single charge. But in 24 hours, if you do opportunity charging or in-route charging, that same customer, Antelope Valley, has seen up to 740 miles in a 24-hour period. So depending on how you opportunity charge the car or the vehicles, you'll see a larger range. We recommend a 3 to 6 hour overnight AC charge. We do direct AC charging to the bus. We use the same inverters for regenerative braking that we do for charging. So we're able to deliver AC directly to the bus. And because we use in-wheel hub motors, we can drop the floor of the bus very low. We don't have an axle that goes down the middle of the bus or a transmission, so we can lower that floor of the bus very low. So it's very passenger friendly. When we were asked about our design philosophy and how does it work, we start off with looking at, no one can disobey the law of conservation of energy. So we want to keep it as simple and flexible as possible and reduce all the losses. So obviously we've got electricity from the grid. We want to provide that to the traction and traction motors as directly with as few losses as possible. So BYD has developed an in-wheel hub traction motor, electric motors that go right in the hubs, and we're delivering that battery power from our batteries on board the buses directly to those in-wheel traction motors. We don't have an engine. Clearly that's replaced with the motors. We don't have clutches or drivetrains or transmissions, and therefore we can reduce some of the friction losses. We also believe we reduce some of the heat loss that occurs when you're going through charging, and that's why we recommend a slow charge. Now, iron phosphate chemistries are non-exothermic batteries. That means they don't really develop heat when they're charged or discharged, but what does develop heat is conductors, resistance in the connections. And so charging at a 0.2 C rate over 3 to 6 hours reduces your heat loss, and it does reduce some of your chemical charging inefficiencies. So while the iron phosphate chemistry is capable of a fast rate charge, up to 3 or 4 C rate charge, we recommend charging flexibly when you have the power available, and slow charging so you can reduce the heat loss through the inverters and reduce those or increase the charge efficiency. This picture shows a interface that we have. That's a 480 volt 3-phase interface, and we actually give the customer an option with 2 nozzles or 2 plugs. The first plug plugs into about 40 kilowatts of inverters. So from the grid, you're still 480 volt 3-phase, but you plug into a 40 kilowatt charge. If you plug the second nozzle in, you're charging now the second 40 kilowatts, so you're charging at 80 kilowatts. That way you can manually manage demand rate charges if you wish. If you don't have a problem, you can plug in both of the connectors at the same time. The interface allows the 480 volt 3-phase up to about 100 amps. We have an interface that allows up to, I think, 150 amps. So we can do faster rate charging depending on the customer's requirements, but we do recommend an overnight charge when the peak rates are lowest. or the rates, power rates are the lowest. And if you look at the transparent bus image, I just kind of show that we have 3 areas where we house battery packs. So we have 3 independent packs on the bus. If you have an issue with any individual pack, you have 2 other sets of packs that still can operate the bus. So they operate together, but they are independent packs. We have up to 24-hour bus operation. We have 324 kilowatt hour. We have buses that are coming online that have 360 kilowatt hour for a 40-foot bus. And again, this allows for flexible charging when you need to charge when the bus is out of service or off-peak. And we believe by allowing this flexible charging, you're reducing your ratepayer cost. Peak capacity is not increased. You don't have to charge during peak rates. The utility capital is amortized over larger energy spend because now you have this transportation, electrified transportation, that's using this energy at night when the grid is at the lowest and very available. And then we also believe that a lot of times nighttime energy costs can be lower, and therefore you can reduce your cost to charge. And then because the BYD vehicle accepts a direct AC at the bus, we reduce the DC line losses, and the interface is very inexpensive. So literally the infrastructure cost to charge the BYD bus is $8,000 a bus, and we actually include that power interface in the price of the bus. So it's a very, very low-cost way to charge buses. Because we have AC charging and we have bidirectional inverters, you can actually do AC discharging from the bus. And so you have the benefit of having bidirectional charging and using the regenerative braking benefits. So that's kind of our design philosophy. Presently, we have mostly 40-foot shuttles, 40-foot transit buses operating, and we have about 154 million miles in revenue service across mostly China is where those revenue service, though you'll hear later on about some U.S. revenue service. We have a 30-foot shuttle. We have a 60-foot articulated bus. And we've designed a low-floor option out of the United States that we built out of our Lancaster, California plant. That's where most of our U.S. manufacturing is done, is out of California. We have completed testing in very cold climates. We were in Montreal last winter during the polar vortex. We were able to demonstrate the iron-phosphate chemistry operates very well in cold temperatures. We finished our Transport Canada certifications. We're the first 40-foot electric bus to get CMVSS approvals from Transport Canada, and we've completed Altoona. We're the first long-range 40-foot bus to complete the Altoona testing. We have also have several now. This release was from our Antelope Valley customer, talking about the 24-hour record they set with 746 miles over that 24-hour period. And they charged the bus a couple times, I think 3 or 4 times, and achieved about 240 to 256 miles each time they charged the bus. The total cost of ownership, we believe, is less expensive by far than a diesel bus that replaces our natural gas bus. We believe you can save anywhere from $200,000 to $400,000 over 10 years. If you extend that to 12 or 15 years, your savings grows clearly because your fuel cost is very inexpensive. And then coming soon, we will have the shuttle built out of Lancaster, California, the 30-foot shuttle, and the articulated bus. We'll have an articulated bus at the Houston Expo that we'll be showing. We'll be revealing there, and that bus will then go on to Altoona for testing. And that will be the first 60-foot battery electric articulated bus to launch in the world. So we're very excited about that being built out of our Lancaster, California plant. A little about our bidirectional charging and discharging. We can literally charge a bus from one of our electric taxis, or you can do vehicle-to-vehicle stranded vehicle assist. Electric buses can charge other electric buses. We have taxis in the Huntington Beach ride and drive today that are demonstrating our vehicle-to-load. They're powering some coffee makers, I think some popcorn machines directly from the electric taxi. So by a press of a button, you can enable the electric port to now discharge 240 volts, 30 amps from that charge port. And then we have at our site in Shenzhen shown vehicle-to-grid, though we haven't seen any vehicle-to-grid operations with our buses in service. So that's what we call vehicle-to-grid ready. And then electric taxis, number of electric taxis using the same module, same iron-phosphate energy module. And we're kind of letting these markets drive some of the scale for our iron-phosphate chemistry. And when you look at the iron-phosphate modules, we believe they're probably the most environmentally friendly chemistry available. There's no caustic materials in the manufacturing process. There's no heavy metals, no toxic electrolytes. They literally can be disposed of in a landfill. There's nothing that can harm the environment. It's rust and soap. And we believe because of the cycles that we can get out of an iron-phosphate module that will not even be halfway consumed at the end of the bus life or these taxis. And we have taxis now that have ran all through their life cycle of 5 years and have over 350,000 miles that they've ran over those 5 years, and still have over 80% remaining capacity. Now with that remaining capacity in an iron phosphate module, we believe you can repurpose it. And we have examples where we're using it for home energy storage, for renewable balancing. We're repurposing batteries for fixed energy storage, for grid tie storage, and we see that becoming a very large market. And it's kind of nice because BYD is their own customer for these products, where we can recover them from the taxis or from the buses and then put them right into fixed energy storage. And then after 30 years, when these fixed energy storage assets are now to the point where they are no longer usable, we can make a decision whether we need to recycle or can recycle some of the copper foils or whatever is valuable in the batteries, or dispose of them. So it's a very unique cycle life of iron phosphate. So that was my last slide. Katie?
Thank you, Michael. I appreciate your participation today. We'll go ahead and pull up Ward Thomas's presentation. Ward Thomas is with transit operations at Stanford University. The Stanford Marguerite, the university's first transit service, currently operates 13 40-foot electric buses on and off campus, providing free service for the faculty, staff, and students in the surrounding community. So Ward has been involved in the transportation industry since 2000. He worked for Bowers Transportation, Google, and now Stanford University. He designed and implemented expansion of Google corporate shuttle program from 4 shuttles to over 35 in just 1 year, serving over 2,500 riders daily. At Stanford University, he is charged with the responsibility for the Stanford Marguerite, which is, again, a public transportation service that services nearly 2.7 million riders annually. Now with 13 100% battery electric buses, and they'll add another 10 in early 2015. So Ward, we'll go ahead and turn the presentation over to you. Thank you again for joining us today, and we look forward to hearing your presentation.
Thank you very much. Good morning and afternoon to everybody. My name is Ward, once again with Stanford University. Here's a picture of our battery electric bus on our main quad looked at Hoover Tower. Just talk to you a little bit about Stanford Marguerite. We were founded before 1976, but Parking and Transportation Services took over the service in 1976. It's a huge part, our transit system is a huge part to decrease our single occupant vehicles to campus. In 2002, we started at 72%, and today we're just over 46% single occupant vehicles coming to campus. We have a fleet of 79 vehicles, 2.3 million riders in 2013. I think we'll be about 2.7 in 2014 million riders. We have 110 drivers and staff and we do about 2,500 charters annually as well. Stanford Marguerite covers a pretty wide footprint. Most college or university transit systems just cover their campuses, but as you can see from the map here, since we're in Northern California, in between Silicon Valley and San Francisco, you can see that from the map that Stanford's got a lot of gray lines around it, but we go all the way over the East Bay. We also go to Mountain View, which is deeper into Silicon Valley, and north up to Menlo Park. Our job is to take care of our students, faculty, and staff with core campus, off-campus, and then transit-based services. And we also have partnerships with various transit agencies in the area. Here's a look at our fleet. We're pretty diverse. We go from 14 to 16 passenger sprinter vans all the way up to 57 passenger motor coaches. We have diesel as our primary driver to fuel all the vehicles except for electricity for our new battery electric buses. We started off our electric bus program as a pilot project to get to learn a little bit more about electric buses, figure out how they operated, make sure they're the right fit for Stanford. We had a few goals in mind. We wanted a bus that would go all day long for us. And for us, our range daily is about 125 to 145 miles a day. We want to be able to take the opportunity to charge at night. We need to be a low-floor bus, ADA compliant. We wanted to lower our long-term costs, which I'm going to show you later on about that. We wanted onboard charging infrastructure versus putting in chargers all around campus. Stanford's likes to make sure we have a very beautiful campus, and we didn't want to put a whole bunch of chargers all over the place. We wanted something that was easy to maintain and well supported. There's a lot of things to consider if you're thinking about going electric, especially in the transit space. You got to look at the reputation of the company. You've got to see what kind of components are part of the bus, what kind of financial resources the company has, are there going to be parts available, how many vehicles on the road, what are different charging options. There's a whole laundry list, as you can see here, of things we had to look at before selecting a vendor. Here's the good stuff that kind of really shows how this makes sense if you're involved in transit. We do have 13 buses right now at Stanford, and they're roughly on 10 routes. But our initial project started out with 3 buses, and those 3 buses did just under 2,300 miles a week on 3 routes. And if we did a cost comparison against our hybrid buses that we have, against our diesel buses, and then obviously electric buses. So as you can see here, the fuel cost for a week with a hybrid bus is about $1,500, and then almost $2,500 a week for a regular diesel bus. But for the electric buses to charge up was just over $500. So that's a 3 to 5x difference in costs. And that, at the end of the day, comes out to a lot of money. So here's charts put together by a different organization to kind of show how the bus performs all day long on our routes. We've got the initial 3 buses that you see here were our buses 34, 05, 06, and 07. The chart's at the bottom of the screen there. And you see the performance of 3405 is not as good as 6 and 7. And what we determined was that we had an inverter issue with 3405, which has been replaced, and now it's come more in line with the 6 and 7 buses. So you can see that drive these things all day long, for the most part. Even with a bad inverter, you're still getting 130 plus miles with a bad inverter set. So we're glad that we got that taken care of. It's proven that we can go long, and we can get through our workday without having to recharge. This is one thing I really love to see here. This is our maintenance summary for the buses to date, well, through June 2014 for the initial 3 buses. We've got anywhere from 19 cents a mile to 34 cents a mile based on the various miles that the buses have gone. And this covers our 45-day inspections as well as anything out of the ordinary that takes place. We have had a couple of issues with the buses, simple things like headlight adjustments, HVAC, door adjustments with sensors, as well as some minor electrical things. Buses always made it home to the yard, so there was no issues as far as that's concerned. But at the end of the day, there are these things, and we know that we're going to have these things with any new style bus that we have here at Stanford. Implementation approach. How do we get additional buy-out for these things? The manufacturer gave us a bus for 2 months. We put it on all of our routes. I believe we had 22 routes at that time. And we wanted to explore how the bus performed on a variety of different ranges and terrains. We decided to put the bus onto 4 routes when we did go into the purchase phase. And the bus made it all day long and still had 20% on the battery when it came back in. And the nice thing about the technology that we're using is I've been assured by the manufacturer that I can bring this stuff down to 2% or 1% if we needed to without hurting the battery chemistry. A lot of people would need to bring the bus in 20 to 15%, which is state of charge left on the battery, to keep warranties intact. And we've been able to not have that restriction on us. The biggest goal upon delivery was training our drivers as well as our vehicle technicians. We wanted to gather data, which we do on a daily basis, and our goal is 2 kilowatt hours per mile as our burn rate, which we've done pretty good on. In order to get the administration to buy off on such a large expenditure, we had to put the numbers together. So we took our current cutaway that we're using right this second, and cutaways are good for about 7.5 to 8 years. And if you look at the cost to run a cutaway for those years, it's just under 500,000 miles, or excuse me, under $500,000, or $207 per mile. And if we compare that to a 30-foot electric bus, the cost is $724, roughly $725,000, but we're getting a 15-year bus versus a 7.5-year bus. So twice as long, and at the end of the day, the cost per mile is $161. So 207 versus 161 per mile, a pretty good savings there. We also have to take a look at our hybrid buses and our diesel buses and compare them to 3 different electric style buses. We looked at a 40-foot repower of taking one of our Gillick buses and repowering it with an aftermarket battery and electric motor set. And we looked at that cost for 8 years, and that came up to $2.20 per mile, which is pretty good. And it actually beats the other costs of $236 or $268 per mile based on either a brand new 40-foot or brand new 35-foot bus. So it makes sense for repower buses as an option to take a look at that if you want to extend the life of buses in your fleet or vehicles in your fleet. But we also, at Stanford, we wanted to make sure that we've got the best and the newest vehicles possible. And so that's why we also looked at the 40 and the 35-foot options as well. And these numbers came directly from our life cycle cost analysis, vetted through our lands, buildings, and real estate financial team. And so far, we're pretty young into the stage, pretty early into the stage of the electric bus process, just about a year now. But things are coming, as you can see, from maintenance costs. They're coming up just on target. A couple of options if you're looking at different styles of electric vehicles, electric buses. For us, we use a 2-paddle system, which is basically not even a charger, it's more of a pass-through for the electricity. A handshake is required between the charging unit as well as this pass-through unit here. The charger is actually on board the bus versus sitting on a sidewalk or in our bus yard. To keep energy our own, it's RFID capable, and as discussed earlier, we've got 480, 440, either running at 50 to 80 amps, or we could also, if we wanted to slow down the charge, we could bring it down to 220. Other charging options that are offered out there in the world is inductive charging pads, as you can see in the lower left, where a bus will actually roll over the charging pad and get charged for a short period of time while it's dwelling. And then there's the overhead fast charger, which is part of Proterra's model, which comes in and puts this mechanism on top of the bus, and you're charged up in about 10 minutes. Along the way, we've had a couple issues, so we're very open about what we've got going on. Driver training is the most important piece. I don't know if any of you deal with bus drivers at all, but when they drive diesel buses, they put their foot on the accelerator and they let it off and they go straight to the brake. So teaching them how to take advantage of the regenerative braking piece is very important. And then they also need to control the HVAC environment as well. A lot of bus drivers just kind of set it and forget it, and we need to make sure that they didn't do that. They actually are manually controlling the system. In our most recent buses, we have a good climate control system on where we set the temperature at 68 in the summer and 70 in the winter, and it handles all the fans going up and down, so for better energy consumption. We have to also let our emergency responders on campus and around Palo Alto know exactly how to shut down the bus. And then, as discussed earlier, we've had some HVAC issues, inverter shutdown, some battery management software. We had to tweak that. And these buses are a little lower to the ground, so there's some areas on our campus where we get some tail dragging. And then one of the things at the very beginning, drivers would call in and say, hey, I'm at 20% or 25%, I need to come in and switch out my bus. So there's a little range anxiety at the very beginning, but for the most part, that's been taken care of. Next up at Stanford, as discussed earlier, we're going to procure additional 10 30-foot low-floor transit buses. They have 182.5 kilowatt battery packs on them. There's dual doors. Here's a little picture of it up here in the upper right. Not standardized yet, but you get the idea of what it looks like. We're also looking at repower options for our existing fleet of 14 2004 Gillig buses. And then because of all the work that we've done so far with the trials and everything else, the administration has approved a plan to electrify 80% of our fleet by 2020, which is going to be pretty significant. By the numbers for last year, we had 3 buses in service covering 66,000 miles. Only about 6% of our annual route miles were under electricity. This year, we're looking at just under 500,000 miles, which brings us to 37% of our annual route miles, and then by fiscal year 16, with the 23 buses, we'll be at 58%. So pretty significant to run almost half your miles with electricity. And the nice thing is we have our own power plant here at Stanford, so we get to control our costs. Considerations: if you're looking to go electric in the transit world, you've got to take a look at how many miles you travel each day and figure out which format works best for you. At Stanford, we don't have a whole lot of dwell time between one route and the next, so we chose to go with this format versus others. Battery pack size and range limitations. Different manufacturers offer different sizes. We would need to know if we're going to charge overhead or inductive, and what dwell time is. We have the midlife battery replacement cost as well to consider for some vehicles. We want to take a look at our annual costs, the support infrastructure, as well as passenger capacity. One thing that works really well here at Stanford is our Sprinter fleet of vans, and we'll keep those in place, and that's where we go. That's why we're only at 80% versus going all the way 100% electric. How do you pay for an electric bus? They're expensive. But as you see, life cycle, they're really inexpensive, but upfront costs can be expensive. So there's financing and lease options usually from the manufacturer or from banking institutions. There's some local and state grants here in California that we've been taking advantage of. So if you're a university, there's university improvement funds for capital improvements. And then if you're not and you get federal funds, there's usually a federal funding formula to take advantage of. And really the biggest deal is savings and maintenance costs over the years that you operate the buses. That's it for me. My contact information is in the slide, and then an additional resource that we put up here is a list of different vendors we've talked to about their electric transit bus products. Pretty much, if you're interested, if you know the bus space, you know pretty much about all these guys here. Motive is a new company out of Palo Alto, Stanford grads, who are just putting a couple of new cutaway buses into the market locally with a high-tech firm. So there's lots of cool things happening with all these folks here. And I want to thank you very much for your time. If you have any questions, feel free to write them down, and I'll be glad to answer later on.
Thank you, Ward. This is Katie Dry again. I've been logging all of the questions as we go, so if any of you have questions for Ward or for any of our speakers, please remember to submit them through the Q&A pod on the right-hand side, and we'll be doing questions in just a few minutes.